hopefully you've done your equilibrium activity and you get a better idea what I'm talking about. Again, it's not when they're the same amount, it's when the amount doesn't change. That's when they're at equilibrium. And we can actually figure that out, what that constant is. Remember, when we're doing our constant, like we did our rate constant, we always have our products on top and our reactants on the bottom. And if you know a little bit about each, you can actually determine the other ones. You can determine their final concentration, and I'll show you how. Okay. Again, the equilibrium expression is these are your two products to whatever. This is the coefficient in front of them, and here's your two reactants. And again, this is the product in front of them. Sometimes you don't have two of each. This is just a general equation. Okay. And I'm going to show you later how to do the pressure part of it. It's proportional to the concentration of the gases in a closed system, and again I'll show you that in a little bit later. It's just a equation that you plug in the numbers, and again I'll show you that. This is how you do it. It works out for another, we'll use the gas constant and so on, but I'll show you that a little bit later. Right now I want to get to how to find your concentrations. Okay, as you can see, the ratio of, in this one, we have N2O4 and we have NO2. Okay, we have to put a 2 here. This is the product because again the coefficient here, and this there's no to any power because it's just there's the coefficient here. There isn't one, so it's 1. Okay, so it remains constant at this temperature no matter what the initial concentrations are. Here we've got numbers change, and this is where they hit equilibrium. And see, the K sub C is the same. I mean, here it's 0.211, 0.211, 0.213 to the third, the 100th, 1000th power. If it changes a little, it's not that much different. But this is, they figured it out at each of these times, and this constant is the same. Okay. One thing to remember about K, when you find that equilibrium constant, okay, if the number is greater than 1, it favors products. The activity you did, you'll notice that the number was higher on the product than it was on the reactant when it reached equilibrium. So if we did the K for those activities I had you do, you'll notice that yes, the K would be greater than 1. If K is less than 1, then it favors the reactants. In other words, the reactants are going to be at a higher amount than the products when they reach equilibrium. Okay, so the K, when you figure it out, can tell you about your reaction. Okay, so when we're trying to find it, remember stoichiometry is very important. When we did stoichiometry last in 121, some of you might thought, oh, I'm so glad I'm done with that. Sorry, you guys, it's always there. It's really important to have a balanced equation because we need those numbers when we're trying to figure out our K and our K sub C. And again, it was the same with the last chapter. We have to raise them to the power. That's when we figured out the reaction rates. Okay, so if we're doing these numbers, we got to make sure, and again, it would be 1 and this would be 2. Okay, here's changing the numbers for our K sub C. Again, if we're going reactant to product or product to reactant. But when you're setting up this equation, your product goes on top to whatever power and your reactant goes on the bottom to whatever power. Okay. All right. To show you it again, this equation right here, I want to show you differences. See how we have a solid here and a solid here and a gas here? This is the only thing we would worry about. Our K sub C is going to equal to your concentration of your CO2. So this one's going to be really easy to figure out because these guys, because they're solids, they're down here, they don't change. Okay. The carbon dioxide, because it's a gas, you're going to have more collisions with the particles, and that's all you're going to worry about. These guys, because they're solids, they just hang in their same amounts, and they just, they don't affect equilibrium. Okay. So when we're trying to figure out equilibrium, we're going to use something called a Rice table. Okay. Rice stands for reactant, initial, your concentration initially, your change in concentration, and what your concentration is at equilibrium. Okay, so you're going to tabulate in this table. You're going to tabulate all that: the initial, the change, and the equilibrium. Okay, for anything for which initial and equilibrium concentrations are known, you put them in the chart, and then you use them to calculate the change. Okay, you have to use a balanced equation because you have to use your mole ratios. Okay, when you're trying to figure these out, that's important. So you have to have a balanced equation in order to do these. And you use the initial concentration. So one thing to remember, if you're just starting out your reaction, your initial for your product is going to be 0 because you haven't produced it yet. Okay, and then you calculate your equilibrium constants using all these concentrations. And again, that sounds like a lot, but come back to this page once in a while and you'll see what I'm talking about. Okay, so here's an example. We have a closed system, and that's important. We need a closed system. We have our concentration of H2. We have our concentration of I2, so hydrogen gas and iodine gas, and they've got the temp. It's allowed to reach equilibrium, and we're going to make hydrogen iodide, and that's its concentration. So we're going to calculate the K sub C, the equilibrium constant, at 448. Now, when we're just doing equilibrium, we don't need to worry about the temperature. Later on, when we're talking about pressure, then the temperature comes into play. But for this, we won't have to worry about it. Okay, so there's a balanced equation. We got hydrogen gas, iodine gas, and we get hydrogen iodide and gas. And since they're all gases, they're all involved in our equation. Okay, so here's my RICE table. Okay, I didn't write reactant here, but that's why it's called RICE. Reactant initial change equilibrium. Okay, my problem told me these two guys. Okay, they said what their concentration was. And I know this is my product, so that's why there's a 0 there. I haven't started the reaction yet, so I don't have any product yet. So your product, unless they tell you there's some produced already, is always 0. Okay, I also put in the numbers. And this up here, the concentration needs to be in molarity. Sometimes they'll give you the amounts and you're going to have to calculate the molarity. Moles divided by liters. Okay, so anyway, I used the balance equation to put in the amounts. All right, so the change. Well, the first one I can figure out the change is this guy. Because it goes from 1.87 times 10 to the negative third. That's what they said its concentration of my product was. And it started at 0, so this has to be plus 1.87 times 10 to the negative third. I mean, because if it goes to 0 and it goes to here, that's the change. So it's the difference here. Okay, so now I can use this to figure out these two. Okay, this is, because the change is going to be the same. This is for the product, okay? So what I'm going to do is I'm going to use my mole ratio. I'm going to use this number, and there's 2 moles of this to only 1 mole of this. So I'm just going to multiply by my mole ratio. I'm going to put 1 on top and 2 on the bottom. Because if I was doing a mole ratio, I'd have, this is the concentration, and the moles of HI is 2, and the moles of I2 is 1. So again, I'm just going to take this number and I'm going to divide by 2. And that will give me, and since they're both 1 moles, they're both going to be the same. If it's a reactant, then it's negative, you guys. If it's a product, it's positive because you're making this stuff and you're using this stuff, so you have to negative. So all I did was I took this divided by 2, and that's how I got this number. And again, it's just using the mole ratio. Now all I have to do is subtract those two and subtract those two. And I've got all my concentrations at equilibrium. So again, I got this information and I got this, and I could fill in all the rest, okay? The products are 0, see if it gives you your equilibrium. There you go. And then use your mole ratios to figure out these. Okay, so now I got all the numbers. Now what I have to do is figure out, using that equation, this concentration to the second power over the concentration of these two guys to the first power. Okay, so I fill in my numbers. HI, the concentration I got from my chart was 1.87 times 10 to the negative third to the second power, because there's a 2 in front of it. And then I took the concentration of hydrogen gas and the concentration of iodide gas. And then I just multiplied and divide, and I got 51. So this tells me, if you remember from K, this favors products, right? It's above 1, okay? So that's how you do, oh, I'm good on time. I was just making sure I didn't run out of time. That's how you do a RICE table. Now I'll do another one after this, not as part of the notes, just to give you an idea how to do it. And that's what you're going to do now. You're going to practice doing these. But again, you fill it in using the information they give you, and then you've got to remember to, your change here is based on your mole ratios from your equation. And then you've got everything you need. This is my product, and again, I take it to the second power. These are my 2 reactants. I don't have to take them to any power because there's just one of them. Okay, if there was a 3 here, I would have had to take this number and multiply by 3 and divide by 2. So you just use the mole ratio from your balanced equation, and then you can figure these out. And again, your reactants are always negative. Your product's always positive because you're using these to make this. So you're losing these and gaining this. and then you've got your numbers at equilibrium. This is where the numbers aren't going to change anymore. Okay? And again, remember, equilibrium is when the amount of reactant and the amount of product stays the same. It doesn't mean they're both the same number. As you can see, they're actually 3 different numbers. So don't think of equilibrium as the numbers have to be the same. I know that's hard when you say equal, but this is equilibrium. This is when the reaction, the reverse and forward, are happening at the same level. And that's what you use a rice table for. Okay? They didn't have these when I had to figure this stuff out. When I started doing these problems and I saw this, it's like, awesome. This makes it so much easier. So when I'll do a couple more for you guys to show you how to do them. And then that's all we're going to do this time, because this is, this is a good practice here. So again, I'm going to do a couple more examples. You'll see them as videos. And then you guys need to practice some of your rice tables.